Are you able to read? Should be okay, right? Yeah. So, let me find the folder where I place my codes. Optimization here. Okay. I'm creating a new script. Okay, this is for linear programming. Before you start, you need to decide how the data structure is gonna look like. Let's try to write a general code. But if I write a general code, I cannot plot out all the solutions if I have more than 3 variables, more than 2 variables, because there's no way I can plot a 4D diagram. So the maximum number of variable that I can plot is 2 or 3. In 3, it's gonna be in a 3D space. It's also hard to read. So I guess I can only write a code for a problem with 2 variables. So in this case, I'm gonna use the example that was presented last time, and assuming you already apply select variables, and after you do that, you have several matrices. So you have your C matrix, which is this from the notes last time, and you have your capital A is gonna be let me change the line so you can read them more easily. And here. Okay, so this is the matrix A, and you have a B vector, small b. Let me make a large B, so I won't accidentally use the symbols. So let me just use capital B, and it's 2, 7, and 3. Okay. Typo here. Okay, so it's a vertical B vector. Now there's always decisions of basic and non-basic. I'm going to use a vector to keep a record of who's basic and who's non-basic. So I'm going to call that vector as just basic. Okay, and right now at the beginning we are having let me use 0 for non-basic and 1 for basic. Okay, that's what we start with last time, but in computer I need to define a way to memorize all these. So I'm using this 0 and 1 to let the computer know which variable is basic, which one is non-basic. Okay, so this is like an initial setting. Before I start, I would like to plot the entire problem. So here I'm going to write some codes for plotting. Figure, I'm going to use I need to define functions, so let me use symbolic. Do I use symbolic? Yeah. So let me use symbolic x1 and x2, and then I know my function is going to be the first coefficient times x1 plus second coefficient times x2. And I have three constraints. Let me just call them, in my case, I already know who they are. They are all inequality constraints. Originally, they were smaller than some number on the right hand side of the equation. But in order to make them equality, we introduce slack variables. So before we do this, before we introduce slack variables, they were actually inequality constraints. For the first one, it's negative 2 x1 plus x2 smaller than or equals to 2 right here. So I'm going to write a for loop. There are only three constraints. Actually, later on we can have more constraints. It's okay to have more constraints, but I cannot have more variables. So in order to make this code more general, here I'm going to say size A2. Is it size A2? So A2 is size A2 is 5. Okay, size A1. Okay. So size A1 means the A is 3 by 5. So this means the length along the first dimension. So basically 3. It's a 3 by 5. So size bracket A comma 1. 1 represent the first dimension. So it's gonna be 3. So later on, if I expand matrix A to introduce more constraints, this line will be general enough to collect the information. I don't need to rewrite the code. So I'm going to call my constraint functions as G, and let me see if I can do this. G1 equals to I1 times x1 plus I2 times x2 minus bi. Let me see if I can do. Also should be gi. Look at this. So g. Okay. Yeah. So here, g1 is x2. Basically negative 2x1 plus x2 minus 2. G2 is x1 negative x1 plus 2x2 minus 7. Then the third one is x1 minus 3. All these must be smaller than 0. Okay, now I can plot my figures, my functions. So then I can use easy contour F, and I can choose my plotting zone. Let me make it larger at the beginning. Let's see. Okay, so this is my algebraic function. Let me change the parameter so it looks better. Now I need to get the handle of the algebraic function. So last time it was object find, a find object, and looking for line width 0.5. Okay, so let me call this H. So the second one will be my contour. So set H second one and change the line width to 2. No. Line empty. Not 0.5. 1. No. Why? Line. Oh, because of a typo. Line width. Okay. Yep. So now the lines are thicker. And then I need the axis to be square. So the scale of x and y axes are the same. So it looks more straight, more in the proper scale. Then I would like to set GCA font size 20, set GCF color white, change the background color, and then position, let's say 100, 100, 600, 600. Okay, and I don't need a title, so yep. Okay, so this is my objective function. Now I need to plot my constraints. So I will make my constraint functions solid black color. Okay. So I need to write a for loop. And then easy plot GI, plotting in the same zone. Since we are sharing the same plotting zone, let me define a plotting zone right here. So later on, if I want to change it, I can change it in one shot. So here, this is the plotting zone. And let me define a second handle. So set each one as line width 2 and color black. Okay. I forget to hold on. So when I finish the contour, I need to hold on. Otherwise, what you do afterward will replace your earlier plotting. Okay. So from here you can tell my plotting zone is too small. The colored lines are the contour, and blue represent lower value. If you visualize this, I know the plotting, the feasible region is at the middle right here. So the solution is at the upper right corner. So I need to expand the plotting zone a little bit. Let me make it 15 over here. Oh, and maybe this one, okay, not square, equal. Okay, and and here I will plot until 12. Okay. Yeah. So actually the solution is right here. But we start from 0, 0. Okay, when we define our basic variables, actually we chose our x1 and x2 to be 0. However, there could be problems where 0, 0 is not a feasible solution. Then it's difficult for LP because LP cannot handle any solution that is not feasible. It has to be feasible all the time. Otherwise, it may go crazy. It may find something else. So if you have a initial guess 0, 0, that is not a feasible point, that's another story. We need to handle the problem differently. We need to have some pre-process in order to find a feasible starting point. But in this example, and in all the problems that I give you, I won't give you that kind of issues. Okay? So, the starting point, let me plot the starting point, is actually 0, 0. So let me draw a red circle, marker size 8, line width 2. Okay, so let me make it more obvious. Make it 3. Okay. So this is our starting point, in fact. Now we are going to do whatever that we introduced last time and see what's going on. So meanwhile, I can evaluate the function values just because later on you may need those numbers. So how do I evaluate function values? So basically I have my f. You just substitute 0, 0 to your f. If that's the case, let me define x as my variable. So x actually, I may want to compute all the x at the beginning. Actually, I don't need to. In our example, the initial guess is 0, 0, and what would be my rest of the x? Basically, in A matrix, the first 2 columns means nothing because you are applying x. It's a negative 2x1, so it turns out to be 0. And then x2, also 0. Now you have a x3 equals to 2. So you realize the first b is your x3. So over here, it's going to be your b1, and this is going to be your b2 and b3. So your x3, 4, and 5, they are actually your b vector. Okay? Do I make it a vertical matrix? Maybe it would be better if I make it a vertical matrix. If that's the case, let me just transpose it. Okay? So this is your initial guess. And when I plot, I can actually plot x1 and x2. Okay? Now I need to start my iteration. So I have my x. I can now compute all the functions. So we can study the function values during the iteration. So let me use capital F as function values. And capital F would be substituting small f, and then actually we only have x1 and x2. No, I think I should do this. And then I'm plugging in x1 and x2. So basically x1 like this. Okay. Just checking. No? What did I do wrong? Substituting. Yes, thank you. Now it's should be like this. Thank you. No, still wrong. 1, 2, 2. Right. Because it's vertical, this is horizontal, so I should do this. Yeah, they need to be at the same size, same shape. So I place these as a vertical one, and this is a vertical matrix. Yes. Okay, and then the G values, I can use a for loop, and over here we can plug in the G values. So substituting in GI, and over here I will use my X is vertical. So later on, every iteration I will increase the columns. So for G's, I will make them vertical as well. So here I comma 1. Yeah. F you don't need to do anything. So G1, G2, and G3. Substituting. Okay. So you can also check what are your F. Now is 0. What are your G? They are function values. Yes, they are smaller than 0. Okay? So it means in the first iteration you have a function value of 0, and all your constraint values are all negative. So they are all feasible. We wish the function G constraint values to be smaller than or equals to 0. Okay? So now we can begin iteration. So what we said last time is we need to compute something called a long. Let me type what need to be computed. We need to compute so-called the CN minus CB times AB inverse times AN. This is what we did last time. So now we need to compute this. So we have a matrix called basic. That's the definition of your non-basic and basic variables. We're going to use it to identify which are the CN and CB, which are the AN and AB. So how do we do that? So we can actually say basic, okay, basic index equals to 1 to 5 times basic. And this time I'm doing a dot product, so I'm transposing this. Okay, why do I do this? Okay, I also need non-basic index equals to set difference 1 to 5 basic index. Okay, let me show you what happened. After I have this, I use a vector 1 to 5 to dot product with this 0, 0, 1, 1, 1. So at the end, basic, how come it's 0? No, I shouldn't do dot product. I should do dot multiply. Dot multiply, so not dot multiply. Okay, so transpose this guy. Okay. Yes. Oh no, not the product. So maybe just this. Yes, okay. I need to remove the zeros. So how do I remove the zeros? Just maybe just sort. So just sort it. Just sort basic index. Let me call this temp. Let me just sort here. Sort. And then this will be the second one to the last one. Okay, then my zero will disappear. Okay, let me try again. I don't need this. Okay, so what I did was, no, I need this. Do it again. Not sort, should be unique. Okay. Yes. Okay, let me tell you what happened. I had a matrix includes all the zeros and ones to identify which are the basic and non-basic. Then I use 1 to 5 dot multiply this 0 and 1s. So if you do that at the end, dot multiply is not dot product. It's a unique way to compute to do matrix multiplication in MATLAB. It's called the element multiplication. So you will be operating element multiplication element by element. So you will actually have 1, 2, 3, 4, and 5 dot multiplying 0, 0, 1, and 1, and 1. So what MATLAB produce is actually 1 multiplying 0, 0, 2 multiplying 0, 0, 3 multiplying 1, 3. So this is what you get at the end. It will be operating the multiplication element by element. It's called the element computation. Okay? So if I do that, from 0, 0, 1, 1, 1, I have 0, 0, 3, 4, 5. Then I use unique. Unique applying to a vector, it will find the unique elements. So what unique does is 0, 0, 3, and 4, and 5. It will ends up with 0, 3, 4, 5. I no longer have two zeros. Then I know I actually I should sort it as well. I should sort, because later on the order could be not, the zeros could be at the middle, so I should sort it and then unique. So my value 0 will be always in the front. If I sort it and then apply unique, the first one will always be 0, and then I will end up with 3 index, which are the index for basic variables. So at the end, I took the second one to the last one. So after I did all these, I have this basic index 3, 4, and 5. That helps me to run my code later on. And then I use something called set difference. It's like determining the difference between two sets. The first set I chose 1 to 5. The second set is the 3, 4, 5. So the difference between them basically is 1 and 2. So then I have a non-basic index 1 and 2. Okay? So why do I need those? Because later on, when I try to get the non-basic part from C, I can just say C and bracket. I can say 1 comma non-basic index. That would be my non-basic ones. And this code is general enough, so later on I don't need to rewrite anymore. This line can only be written, just need to be written once. Then I can have a for loop. I can just keep on updating the index. And this line doesn't need to be rewritten all the time. Minus C, 1 comma, the basic index, index, times A. For A, I will have, so every one of them, comma, the basic ones, and then inverse times A, every one of them, and then basic index. Okay, so supposedly this is going to this should be giving me what I want. So I'm going to call these, they are the coefficients in front of the non-basic variables. So let me just call it coefficient. Okay, let's run it for once. So what's my coefficient? -1 and -2, exactly like what I did last time. And then I need to choose the most negative one. So I need to because in our case we only have 2. In the future we may have a lot. Let me just write a for loop for the first one to the last one. So length of coefficient. So but you basically have like a oh no, I don't need to do this. I just need to the most negative one. So the not the minimum one. Let me just write a for loop. So use the stupidest way. If coefficient ith one is smaller than 0, then it could be a candidate. So let me just say candidate. At the beginning, I will say empty. So if it's negative, then I will have a so most negative. Let me just say 0. So if that one is smaller than 0, I will say it could be the candidate. So the ith index is my candidate. And then the most negative value would be that particular coefficient. Okay? And then into the next one, so I need a check. I need a check. So if the particular coefficient is smaller than the most negative, then I will keep that in mind, right? Should be right. So at the end, I should have candidate 2, second one, and the most negative value is negative 2. Okay, so what does the 2 mean? 2 means the second one. Second non-basic will become basic. So candidate, I can comment right here. So the chosen candidate is the non-basic variable to be converted to basic. Yeah, just write it down to remind us. Okay, then we need to do so-called ratio test. So in order to do the ratio test, we need to compute A hat. Let me say A hat. A hat is AB inverse AN. AB inverse AN. Okay? And B hat. B hat equals to AB inverse times B. Okay? And we are only choosing the column in A hat representing the candidate. So since we already have the index from the candidate, so basically the A hat candidate would be A hat. I should choose all of them, and then the chosen one, the candidate. So A hat candidate should be keeping the coefficient that I'm looking for. Since we are in the ratio test, we could be divided by 0. We don't want to divide by 0. So whenever A hat candidate has a value 0, we don't truly perform the division. So here we can write a for loop, and it goes from 1 to the length of actually B hat. Okay, and then if A hat candidate is 0. We do nothing. So I forget. Is it like this? Okay. So the not equals to is, how do you call this? Like a worm. Is like this. This is not equals to. So only if a hat candidate is not 0, then we can perform ratio test. So over here, I also need another candidate. So let me call this candidate 2, and initially 0. So over here, if a hat candidate is not 0, I can perform ratio test. So then the ratio test equals to b hat, the ith one, over a hat candidate, the ith one. Okay, so I need a initial. I need a smallest positive. So then, since I'm looking for the positive one, let me set a super large number. Super large. Only if you are not lucky, you have the smallest positive is greater than this, then you are not lucky. Then you need to rewrite your code and make this number even greater. So if once you have this this ratio that is smaller than only if your ratio is positive. Okay, we only want the positive one. And hold on. How many and I forget. Okay, they all works. If it's a positive one and also it's smaller than the smallest positive, then you can memorize it. So candidate 2 will be I, and also smallest positive will be replaced by the current ratio. So you will keep on doing this until you have the smallest one. So let's run it. Okay, so now my candidate 2 is empty. So something was wrong. Then I need to check what happened. Do I have the A hat? Okay, let me check my A hat. A hat. Okay, how about A hat candidate? Okay, good. How about B hat? Good. Now I was doing. Okay, where am I? Okay, let's run the debug mode. Oh, it never comes in. So the ith one here. Sorry. Yep. Okay. Now it should be good. Candidate 2 is 1, is it? Yes. So the first, this is telling you the chosen candidate 2 is the basic variable to be converted to non-basic. Okay, now it's time to swap the candidates. So over here we have this value, the ith variable, the ith non-basic. So I have the index of non-basic, this one. So the ith one. This is basically non-basic is 1 and 2. So the ith one. But the ith one basically is this index candidate. So basically the second one over here. So this is the index to become 1. And we have this matrix, basic. So basic, that particular one should be 0 at the beginning. So this should become 1. Okay. And then for here, so we just do the same thing, but the basic one and candidate 2, and this becomes 0. So let's see if that's right at the end. So what happened was my x2 was 0, now become 1. And my x3, which is the first chosen one in the basic, and now it's swapped to non-basic. So x3 becomes 0. So all I need to do next is to form a loop and repeat the code until you cannot find candidates anymore. So up to here, this is first iteration. So what I need to do is move on to the first line right here. So I need to have a while loop. While. So I guess I can take this candidate I guess I need to compute this before I jump into the while loop. So that means I need to compute this at the end. So I will be computing this coefficient at the last line. And I will be let me think about it. Every time I will jump, or I will just say while and while 1. So it's a infinite while true. No? Oh yes, while 1 is right. So it's a infinite loop. Infinite loop. So I just need to find when to break. So if I move back to here, everything, I need to do this again. I need to update the index. So I can do the updating right here. So those will be updated. Then over here it will perform the exact same thing, and it will clear the memory. So after I finish, if the candidate remains empty, it should converge. So if is empty candidate, then break. So this means converged. Okay, let's see. Finished? Yeah, finished. Okay, but I never plot out the results, so you have no idea what happened. But let's just quickly check what would be the final decision. 11100. So from my notes, the last time is 11100. Yes. So it actually converged properly. So now it's time to visualize it. So every time when I find a new set of basic and non-basic, actually I need to figure out what are the variables. So I need to compute. I need to compute for all the x. So let me see. It's right here. The A matrix, everything, and basic index. Basically, this is we have a rectangular A matrix, but if we only choose the basic ones, it's a square matrix. So if I do inverse times B, this actually is the solution for all of your variables. If I remind you by my iPad, let me show you. Remind you by iPad. So here, like in this particular example, these are the ones with non-zero x, and the red ones are the coefficient representing the non-basic variables, basically zeros. So the red columns does nothing. Over here, if you focus on the yellow ones, it's just like doing this. And over here, the corresponding variables that are not zeros. So basically the first one, second one, and the last one. And they equals to 2, 7, and 3. So what you can do is to do x1, x2, and x5, and you can do the matrix over there inverse times this. Then you can solve for 1, 2, and 5. How about 3 and 4? They're 0. Okay, so that's how you can evaluate all the variables at that particular iteration. That's basically what I did. Over here, I'm choosing the basic ones, inverse it, times b. So at the end, I will get 3 numbers. They are the numbers representing the basic variables. So let me just call this guy x, but the basic ones. Okay, and the basic, at this point, my basic looks like what? That's the final iteration already. So what do I have my basic. I only need the x1 and x2, because that's all I need for plotting. But it would be better if I get all the numbers. do I have a container for, oh, I have this x. So x iteration, oh, so at the beginning I should have some iteration number, iter equals to 1. So here iter plus 1, and that particular one, the basic index equals to the answer right here. Oh, so just cut this into here. Okay. So how do I need to define the non-basic ones? No, you don't, because in MATLAB, if you have if you introduce a new column or new row, and if you pick up some items in there and give a value, there will be some other elements undefined. Those will be 0 by default. So we can pause right here to check whether it's right or not. This is a vertical matrix, so I should inverse it. I should transpose it, because I'm memorizing all these horizontally. Am I? Yes, horizontal. Did I? No, I'm doing it vertically, so no transpose. So in this case, I should take this away and do it here. But my basic index was saved horizontally, so I should, do I need to? No, I don't, because this is telling us it's vertical. Okay, just try it. If I run this code, my x, so this is my second after the first iteration here, my variables become 0, 2, 0, 3, 3. Okay, and then I can actually plot the results after I got the values. Plotting the results, that is this line. Okay, I can plot it. Then I would like to compute the function values. So just get everything here. Exactly same code. Yeah, I'm plotting in the, I'm plugging into the original functions in order to get the values. But here I'm gonna say f iter plus 1. G was vertical, so over here iter plus 1. G, yep. So let's see if that works. Okay, now my x, okay, my f, still 0, really? Why? When I plug in, I didn't plug in the, should be iter plus 1. Yes, do it again. So my x, my f. So from here, originally my function value was 0. After the first iteration, it drops to -4. G functions, originally -2, -7, -3, all feasible. Now the first one becomes 0. Second and the third one still remain negative, which means they're all negative or 0 to or equals to 0. They are all feasible. So we are still inside the feasible space. Now let's take a look at the, here I should plot out the first one, iter plus 1, and second one, iter plus 1. Okay, do it again. So from here you can tell it's moving along this boundary, moving up to here, and it stopped. Do you remember last time when we when we introduced everything in MATLAB? And when we introduced the ratio test, it was a little weird when we were doing this. Numerically, we understand there are three linear functions to be satisfied, right? And we are trying to increase the value of x2 while values of x3, x4, and x5 could be changing. They could be remain the same, they could be increasing, they could be reducing, we don't know. But while x2 is increasing, these three functions needs to be maintained correct. And what we did the last time was x2 was 0, and when it increases up to 2, value 2, x3 drops to 0. And that's where we can no longer increase x2, because if I keep on doing it, x3 become negative. And in linear programming, we want all the variables to be positive or 0. So that's where we stopped. This ratio test helped us to stop at this point. But what does it really mean in the entire original design space? In the original problem, what happened was we were here and we never touch any constraint. From the first check right here, when we compute this crazy stuff, not crazy, this long stuff, we chose one variable and we chose the second one, I think. So that means there are two directions to move. If we choose the second one, that means we are moving toward the second one. So we are trying to move along this line by increasing x2, remember? We are increasing x2. We didn't increase x1. So when we increase x2, when we move up to here, one of the select variables becomes 0 and can no longer be reduced. And that's actually where we hit this particular constraint. And if we keep on increasing x2, we will penetrate through that particular constraint. So the beauty of linear programming is that it's helping us finding the direction that reduce function value the fastest. Why this direction reduce function value the fastest? Because over here we chose the most negative one. And we decide to increase x2, so function value should be reducing the fastest. And from the contour gradient direction, you realize if I move toward this direction, it's more steep. And if I move this direction, it's less steep. So linear programming is trying to move along the kind of like a steepest direction. Okay? And it's always moving along the boundary. And the way we design this procedure allow us to stop whenever you hit another constraint. Okay, so let's take a look at next iteration and see what happened. My code should be general enough, so let me just say continue. Okay, so when we continue, you will realize it's moving this particular direction. And it stopped when it hit this particular constraint. Let's do one more move. Okay, it's interesting. Why is it moving up to there? It's weird. So maybe one of the constraint was not plugged. I know why, sorry. Over here, when we plot G, because it's a vertical constraint. And that vertical constraint cannot be plotted properly. So it was not, so maybe symbolic was not the right way to make the plots. Whenever I have vertical constraints or horizontal ones, easy plot will not behave correctly. So I should convert this to string for constraints. So over here, I should do string to number to string, and then multiplying x1 plus number to string multiplying minus number to string. So all my G functions are written in strings. I hope this is fine. Let's see. No. Number to string. Oh. No. Number to string. Why not? Stop right here. Oh, I need this to be a cell. Only cell can contain the whole thing. Yeah. So if there are cells, then when I plot, there are cells. So easy plot. Where is my easy plot? Oh, 26 here. Okay, so this should be cell. Let me see if it truly plots. Yes. So actually, it was a vertical constraint. So how come if I convert symbolic to string, it can easy plot recognize it? Because let's check G3. G3 says 1 times x1 plus 0 times x2. It's a string, right? And it has a text x2 inside, even though the coefficient is 0. So easy plot recognize this as a 2-dimensional function. When it was symbolic, because the coefficient in front of x2 was 0, and it became 0. So the information of x2 disappeared. So when EasyPlot try to plot this function, it will recognize it as a 1-dimensional function. So if it's a 1-dimensional function, it's basically y equals to x1 minus 3. So it's like a tilted line with a slope 1, right? So you want to avoid that, and so one trick is to do this. Okay. So after you program MATLAB so much, you realize how to handle this kind of issue. So I need to make sure what I'm doing here is right as well. And that's it, I think. Okay. No. Okay. What happened? string to symbolic. Let's pause right here and see what happened. No, it was earlier. Where did I? Line 34. It doesn't substitute. Okay. So if it doesn't substitute, then I need to convert it back to symbolic, I guess. But it doesn't convert well. Really? Let's see. Step. Yeah. So let's pause right there again. So G3 subs G1 X1 2 1. Okay. So I need to say string to symbolic. Really? Okay. So over here, string to symbolic. In the past, there was a version of MATLAB will convert this automatically. Okay, now it should be okay. Yep. So after first iteration, it moved to here. Second iteration, it moved to here. The third one, it moved to here. And we can step in and check the coefficient. We compute the coefficient, and this time it's 1 and 2. Remember, in the first check, we are looking for the most negative one. So in my for loop right here, it will not jump into this line because all the coefficients are actually positive. So it will stop right here, and this variable candidate remains empty. So if it's empty, it will break out of the while loop, continue, and finish. That's the procedure. So let's plot out the text information in the command window. So over here, let's say display initial gas equals to so basically 0 and 0. It's always 0 and 0. We can only handle this. And function value equals to number to string f, and then comma, and the g functions. Just say g's. Just say g. And it's a vector. So over here I'm going to number to string and all the g's. G. So over here g, everything 1. It's vertical, so horizontal. Transpose it. Okay, let's see. No, something was wrong. Here. Oh no. Okay. No. Number to string must be numeric. Okay, so it was symbolic. So I need to evaluate G. So it becomes numeric. No? Maybe it's because of F? Yes. Okay. So initially 0, 0, function value is 0. G function values are those. Then as as the iteration moves on, over here I'm gonna plot the values right here. Number to string. So my x, I'm plotting out the x was vertical. So first and the second one, iter plus 1. Oh, I forget to plus my iteration number. Okay, so I should do that. Iter equals to iter plus 1. Yeah, after everything happened. So I'm plotting out my x, it was vertical, so I'm transposing it. Okay, and then my function values, I'm plotting out the iter plus 1, g's, iter plus 1, correct? Where did I miss? Let's see. Yep. 3 brackets. Okay. How about earlier? Number, okay. So here, 2, 3. Okay. Okay. Try it. Okay. Here. Okay. So second iteration, 0 and 2, function value decreases. Now 1 and 4, function value one and 4? 3? Okay. Okay, and 3 and 5. No more. So 3 iterations. 1, 2, 3, yeah. So I should say iter equals to number to string iter minus 1 here. Okay. No, I put the bracket, comma in the wrong place. Okay. I don't need minus 1. Just like this. So 3 iterations. Okay. 0, 1, 2, 1, 4, 3, 5. Okay. Let's try to make this problem more interesting. Let's add one more function. So I can say there's a horizontal one, and function value is around, let's see, this is 5, so maybe 4.5. So let's say x2 must be smaller than 4.5. So if that's the case, I add one more constraint. x2 must be smaller than, so 0, x2, so here 1. And must be smaller than 4.5, so here 4.5. But I'm introducing one more select variables. So I will need one more 0 in C, more zeros in those constraints. Supposedly it will work. Here. Originally I said 1 to 5 here. Now it's actually 1 to 6. So this number 5 should be changed by the size of a comma 2. So it will become a general code. Okay? And I think I can plot from in the region over here. So maybe 0 to 9. 0 to 9. Let's see. Go. something's wrong. Size A2, size A and 2, so 6 of them. The basic ones. Basic ones, I have one more basic ones. Go. Something's wrong. 7, 1 here. So this is size A, comma 2. Size A, comma 2. Go. It went too fast. So whenever I plot out the point, here? Let's say draw now, you will see it. Not here. Draw now this guy. So you can see it. It's very fast. So I need one more iteration, a fourth iteration, because it's moving here, 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 and here. So it will stop here. How about if I change the slope of the object function to make the right hand side be the steeper one? So let's make linear programming move toward right. In order to do that, I need the slope to be like this, more vertical. So in this case, I can say -5. So let's run the code. See? Because moving toward x direction is dropping the objective function value faster, reducing it more. So this time linear programming chose to move toward x1 direction. And luckily there's no constraint over here, so this is first iteration, and then second iteration it reaches to the optimal solution. So only 2 iterations. Okay, but at the beginning, when we start right here, we never know how the constraint look like. So we don't know whether we will bump into. We don't know how many constraints we will bump into. So in fact, if I move toward right hand side, I only need 2 iterations. But all LP knows is the slope. It realized, okay, if I move toward x1 in this case, it drops function value faster, so I should move this way. And let's say I have a bunch of constraints right here, then I may need a lot of iterations. Okay, so this is linear programming. I hope the code, the go through of the code, I should say the walkthrough. I walk through with you, starting from scratch. And if you follow what I did, you should be able to understand what was taught last time, even more. Okay. In the following weekend, we will have a take-home exam. I will ask you to solve linear programming problems. There will be a bonus problem. But the bonus problem is gonna take a long time. Should I include that bonus problem in the? Let me think about it. We still have time, right? Okay. So let's just solve one problem in your take home. So I'm gonna include what I want to do inside the problem. So what's that? What's the thing I'm trying to tell you? Let's take a look at let's create a problem in iPad so you can experience what's going on. Let's go to iPad. first. Now, so last time I talked about something, I mentioned something called sequential linear programming. Sequential linear programming. Okay, so-called the SLP. So in the exam, I will ask you to try this. So what happened is we can try to minimize a problem like this. Let's say x1 minus 5 squared plus let's say 2x1 minus make it larger minus 10 squared plus 5 times x2 minus 8 squared. For example, there's a nonlinear quadratic problem subject to we can have nonlinear constraints as well. So let me make something like this and this. So it's a circle. It's a circle. So should be. Let me draw a picture. So here is 10 and 8. So it's gonna be like the minimum point of this function looks like this, and the contour looks like this. So I'm trying to make a constraint like this, and another one like this. So let's call this G1 and this G2. So G1 should be something like x1 minus, I guess, the center probably here. So this could be negative 10 and 10. So the radius probably is 15, I guess. Okay, so if that's the case, plus 10 squared plus x2 minus 10 squared minus 15 squared is smaller than 0. Okay, the other one, the center looks like here. So this could be, for example, 8 and negative 15, like this. So the radius could be 20. Okay, so x1 minus 8 squared plus x2 plus 15 squared minus 20 squared is smaller than 0. Okay. So, there's an issue because everyone is starting from 0, 0. Okay, that's fine. So, I need to do Taylor expansion. Taylor expansion. Everyone is doing Taylor expansion at 0, 0 because we start from 0, 0, right? So my f linearized will be plugging in, so negative, so this is 100 plus 5 times 64, right? Plug it in. Yes. And then first order Taylor expansion. So plus x1 minus 0 times gradient. Gradient, so it's a 2x1. Oh, 2 times x1 minus 10, so 0 minus 10. Plus x2 minus 0 times 10 times 0 minus 8. So at the end, I would have 420 plus negative 20x1 minus 80x2. Okay? Now, my G1, linear-wise one, will be plugging in zeros. So 100 plus 100 minus 15 squared plus x1 minus 0 times the gradient. So should be 2 times 0 plus 10 plus x2 minus 0 times 2 times 0 minus 10. So at the end, it's 200 minus 15 squared. So negative 25. And this is plus 20x1 minus 20x2. Right? Yeah. So my G2 would be, G2 is right here. So 64 plus 225 minus 400. Plug in 0, right? And then x1 minus 0 times the gradient. 2 times 0 minus 8 plus x2 minus 0 times 2, 0 minus plus 15. So supposedly this looks like 64 plus 225 minus 400. That's fine. That is totally fine. Minus 16x1 plus 30x2. Smaller than 0. Okay? So from those, you can already do linear programming. Let me quickly jump to MATLAB and see what's the result. I'm sorry, when you do the take home, you need to do it by hand. But for me, I have MATLAB. So in that particular case, I'm going to just hide those. I don't want to erase those. I'm just writing a new part of this particular example. So negative 20, negative 80. I will need two select variables, so 0, 0. The A matrix would be 20, negative 20, 1 and 0. Oh, and the other line, minus 16, 30, 0 and 1. My B would be 25, 1, 1, 1, vertically. Okay, if I run the code, my basics, okay, let me just cut this one. Keep that here. So I need to redefine my basic. The basic ones would be the last two, the select variables. Supposedly this code runs well, but I need to define my plotting zone. Let me make it larger, for example 30 and 30, just to see what's going on. Something is wrong. Okay, my code was not general enough. So I should make it general. So just B. B was vertical, so make it horizontal. Yep. So initially it moved up and moved up to here. So what's my solution? This is my solution, right? So sequentially, I should perform linear approximation at this particular point again. So when you do your homework, you did the hard job by hand. At the end, you get the optimal that is 10.6, 3.36. And sequentially, you need to check whether it's converged. So you do the convergence check. Yeah. Sorry, I didn't show the MATLAB. Show the iPad. Sorry. Here. So from linear programming, you got the solution. And you need to check whether the entire process is converged. So we always compare what you get at the end with what you start with. What you start with was 0, 0, right? So it was definitely a large number. So not converged. And you are moving on to a new round of solution process. So this time, like it's a sequential approach, you will do first order Taylor expansion at this point, and then do the whole thing again until you get the solution, until it converged. Until converged. Do you want to see how this can be done in computer, in MATLAB? Only one person not. How about others? Do you want to see? Okay, thank you. This is like giving you the solution. Last time, I gave you several codes, but I realized some of you didn't do well enough in the exam. So this time, I'm giving you more help. Okay, so at the end of the semester, you cannot comment on my rating, say, the professor didn't help me. You can only comment, I didn't study hard enough. The exam was take home, but I didn't do a good job. It's all my fault. Okay, just joking. Anyway, so if I want to make this a sequential code, it's not easy. It's can I complete it within 1 hour? Because that means I need to write a code to do Taylor expansion. So I may need to write a different code. So if I want to do that, let me save this as a different code. Let me call this LPO2. In this LPO2, I'm converting this LPO2 into a completely different code. It's a function, LPO2. Okay, Over here, I will plug in my C and A and B as inputs. So over here, I don't need these. How about basic? Basic. So basic. We can only solve for two-dimensional problem with any number of slack variables. So we basically have basic equals to 0 and 0, and then a bunch of ones. And the ones are basically having the same length, same amount of equations. So size A and 1. So my basic is always like this. And I think that's it, right? How about B? Yeah. I think that's it. Okay. So I just need another code to generate C, A, and B. And this code will produce the result. Once I get the result, I will send it back to the original function. So I will call that X star. So my X star would be the last one. So basically the X was the vertical one. So first and second iter. So I send back a vertical vector. So in my main code, I need to write everything. Maybe I write everything as horizontal. So let's try this. Let's try this. Let's try if there's a bug. So, let me just clear this, close this, and run the code to check whether I have a bug. Okay. So now this linear programming code becomes a function. I can always put CAB into it and get X star. Then I need a main code. So this is the main code for sequential linear programming. So let me call this SLP01. Over here, I need to define my objective function. This time, do I do symbolic? Yeah. So since x1, x2, so my objective function, yeah, that's fine. So over here, symbolic, x1 minus 10 square plus 5 times x2 minus 8 square. My g functions, since they're symbolic, so I can use this g functions x1 plus 10 square plus x2 minus 10 square minus 15. G2 over here, x1 minus 8 square plus x2 plus 15 square minus 20 square. Okay. Now I need to linearize it. So let me call this iter1 and initial point. I said I want to do it horizontally. Maybe I do it vertically, sorry. Vertically. So my x should be 0 and 0 vertically at the beginning. That's my expansion point. And then I need to generate, I need to get all the C numbers and stuff. So the C's, I should define something called error, which is large, while error is larger than 10 to the power of -3. I keep doing it, and then every time I increase my iteration number, over here I will perform Taylor expansion, first order Taylor expansion. So my C would be, the first one will be is symbolic. So I can say DIFF F, and then X1. No, just X1. Just hold on. Let me check if it's right or not. Just pause here. DIFF Fx1. Okay. So this is first order derivative, partial derivative with respect to x1, and then I substituting into this, and x1 use the first value. X, I'm having vertical ones, so the first one, and iter, yep. Okay, and moving on to the next line so you can see this more clearly. Now I'm doing, sorry, I should do this, because after you perform partial derivative, your objective functions could still have x2. So here it should be 1 and 2. 1 and 2. So that gives you two numbers, C1 and C2. And then I will need a bunch of zeros, and the length is a horizontal one, and the length will be your number of your constraints. So length of G. Let's see if you get C. No, something's wrong. Substituting. Okay, let's pause here and see what happened. After derivation is this, and substituting. There's no x2. It doesn't allow me to substitute, really? Or am I doing this right? Yeah. That's why sometimes I don't like symbolic, because it's a first order function. It does. Column. Okay. Oh yeah. Right. Let's see if that's the problem. You're right. Step. Yes. Thank you. Very good. So let's stop here and see how the C. Yep. So did we have negative 20 and negative 80? Exactly what I did. Okay. Now I need a matrix. A matrix. A would be, I need a for loop. 1 to length of G, and then basically Taylor expansion of those. You can just do this. But this time you are doing derivative with respect to Gi, and this will be your A. I don't want to use I cannot. Yes, I is fine. So this will be the ith line. Yeah. So Gi, everything should be the same. Yeah, and then I I will need a identity matrix. So I will do the identity matrix afterward. So once I have everything, A equals to A and I's. I remember I's is identity matrix. No, just I, no S. I is the identity matrix because capital I, right? And the in MATLAB is EYE. The size will be the length of your constraint. Let's see. Oh, I didn't close. I should close here. Okay. So what is your A? Exactly what we did, right? Negative 20. Yep. Exactly what we did. Almost done. B would be. B. We need to. Let me see. B is an issue. B is B basically is plugging in. No. Sometimes if we have different functions, we may generate. Let me see. This is partial derivative. Oh yeah. B is the just plugging in your G, just plugging in. So B is basically this guy. And then I need a for loop. So I can compute B in the same loop. B, we need B to be vertical, so if1 equals to, just substitute into the function, but no need to do derivative, just substitute. Should be it. That should be. Yes. Good. Now you just perform LP underline O2, C, A, and B. And the solution would be X, 1 and 2, ether plus 1. And then you need to check error is norm, the new one minus the previous one, so just ether. Okay. I think it's done. Let's pause right here every time. Okay, something's wrong. Line. Okay, something was not numeric, so I should evaluate this guy, I think, because it was symbolic. No, maybe everything. Just evaluate everything, because everything was symbolic. So I did. Oh, after substituting, evaluate. Just make everything numeric. Try again. Okay. Line 51. Line 51. Line 51. No. Line 74. Line 74. Basic. Line B. B was my B vertical. B. Yeah, vertical. Let's pause right here. B is vertical. When we jump into here, then pause right here. See what happened. B, vertical, basic. Seems to be okay. Dot power. How come? So let's. Something was wrong in the second iteration. You can check why. First iteration, okay. The second iteration. Okay, basic. Okay, something was wrong. When we update, okay, we may need to check right here. Quit. Here. So basic 3 and 4, 1 and 2. So when we update, something was wrong here. Maybe we move on to there. Okay. 1 and 3. 2 and 4. Okay. So the first time was okay. Continue. So let's step in. Basic becomes here something was wrong. One, two, four. Basic. Candidate. Non-basic. Candidate is 1, candidate 2. Oh, candidate 2 was empty. How come it was empty? there will be situations where we didn't meet this guy. So let's see what happened. Okay, so this time, that there's no overlapping. How come? When got it. I'm missing a negative sign here for the b's. B's substitute because it's on the right hand side of the function, so I should put a negative sign here. Yep. That will avoid the problem. Okay, continue. Yep. That's where the problem was. Okay, well, now what? For the let's see. For the second round, let's stop right here. Let's run it. Okay. So error was large. X, I have a new X. I will move to the next iteration. X iter now is 2. So I'm plugging in. Okay, this is fine. So this is good. Now this should be fine. Oh, how come? Unable perform blah 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 blah. Cause I guess I need to recreate A, cause A was so every time I need to clear my A matrix. So let me just clear C, A, and B. Yep. Because over here I'm computing a square A and then expand to make it longer to introduce the slack variables. But in my code, in the second round, this code will violate the shape, the rectangular shape. So it should be okay now. Yep. It's not going to stop. Okay. Hold on. I'm doing a Taylor expansion right here. Then when I go in, I'm solving from 0, 0. So here, yeah, it should converge, right? Because the next time I reach to a point right here. So let's check, let's see why. Okay, the first time error is large, yes. Second time, oh, how come it's 0, 0? Iter now is 2 plus 1. So C is this, A is this, B is this. In the new maybe every time when I plot, I should make a separate plot. So I will throw the iter number here. But outside, let me just call it figure ID. But in fact, it's my figure ID right here. But from outside, it's my iteration number. So we can separate the plotting. So let's do it again. This is the first one. It looks great. Second one. Where are the constraints? So in the second iteration, G is A matrix, B vector. They all have, so we need to see why. Maybe I need to plot out the zone larger just to see what happened. So the zone, let's plot out very large. Just break it and then start over. First one is fine. The function disappeared. How come the G function disappeared? Maybe I changed the function a little bit. Second one, I move to 5 greater radius. Yeah, let's try this. Okay, second one. What happened? What's my B right now? For some reason, how about my G? G is different. When I substitute, am I substituting to the right point? Let me see. Iter is 1. X. I'm using the first column, yes. Now iter becomes 2. When I move to here, I start over again. My X has 2 columns. I'm using the second one to do expansion. Second one. Yeah, none of them is wrong. Then I can move on to here. Iter is 2. But my B is weird. How come my B is like this? G. If I truly plug in this number, let me truly try it. This function substitute in. Let me just truly compute it. Compute. Yeah. How about G2? Yeah. Why? I have two circles. They make linear approximations. And I move on to a new place. And when I plug in the function again, they all give me the same function value. What does that mean? What does that mean? Okay. Go back to MATLAB. Go back to iPad. Think about what I did. So I had two circles. I want my solution to be within this region. And I have a contour like this. So suppose the solution is right here. And then I chose an expansion point somewhere here. I made Taylor expansion of the function, so actually it's like making approximations like this. And my objective function would have something like this. So it ends up with some point right here. And when I use that new point to serve as my new approximation point, it gives me exactly same function value. Why? Okay. I don't know why. I cannot think of a reason. Does that mean I need to make my take-home exam easier? Yes. Otherwise, we may bump into all kinds of issues of those nonlinear constraints. Okay. I guess what I can do is we can solve for nonlinear functions with linear constraints. That will reduce a lot of issues. So let's choose to solve nonlinear constraints, but nonlinear objective functions, but linear constraints. And let's see what happens. So let's have some linear functions here. I can actually use what I had earlier. The problem we had, negative 2x1 plus x2 minus 2. So get rid of this guy. Negative 1 times x1 plus 2 times x2, negative 7. And we had a third constraint, which was x1 minus 3. Okay? And we are, I hope this code can handle it. So let's see. Okay, let's just change the function a little bit. Just plus, just 0.5 times x2. Did that work? Okay, okay, hold on. change the plotting zone. Okay. Okay. If we do expansion, right here, it should not do anything to our. Okay, I need to check what's going on for the second round. This first round is fine. Second round, C is different, sure. B should be the same. -1, -1, -2, 1 and 0.5, yes. B, the problem is B. If we okay, so we should have more terms right here, not just negative g. We should have the x minus Taylor expansion point. Okay. So x minus expansion point. So here I should have negative the expansion point. Expansion point should be actually I can just do, after substituting, minus expansion point should be this guy. Minus expansion point, first one, it was a minus, so now it's a positive. Minus, yes, positive. Expansion point times the gradient, missing this part, times the gradient. So this is the gradient. Yes. Okay. And then second one. So second one, yep. Let's run it again. B is the same thing, yes. Run it. Line Y, B. Okay, I need to do evaluation afterward. I need to do evaluation, evaluating the whole thing. Okay, so do it. Okay. Now B should be the same. Yes. Okay. Converged? Yeah, converged. Did anything change? Same constraint, but you can tell the objective function change its slope a little bit. So, but we're using the same constraint, so the solution is the same. That means I can solve what I had earlier. I should be able to solve what I had. Scary. Hold on. Something must be wrong. Okay, let's show the whole thing again. Let's see what's going on. Oh, not here. Let's pause. So every time it actually stopped at 0, 0, is it? No. Here. Initial gas and get this point. For the second round, it was like this. I'm interested in how the second round looks like. For the first round, everything is fine. And let's take a look at the second round. The B is B. So what's weird was the second round. This is the first round. B was 25 and 375. Now the second round. B is weird. What is my B? 800 something and 1,000. How about C? C is fine. A, after this line, A is like this. Okay, so jump in. So C, A, and B. Okay, let's debug until here. So the function looks like that, and let me draw the original circle just to see how the circle look like. Original circle. So every time before here's the circle. So just in order to see what's going on, extra plotting, easy plot these two. Zone. Just to see. Okay. The circles are small. Okay. I need to change the color of it. Change the color. Change the color. I can give a handle. So set. Let's use a different number. It should be. Let me make it red. Color red. And what do I do? Line width 2. Okay. I guess I make the first circle larger, so U35. Let's see. Okay, so these are the two circles. Is the radius larger? No? Let me make it even larger, maybe 55. Sorry. 35. I need to manually change here. Okay. Just to see. This is no good, too large. Maybe use 30. Okay, 30. Okay, so we're trying to find solutions within those the intersection of these two circles. Actually, the solution is right here, 20 and 4, something like that. But the linear approximation was not accurate, so we end up with somewhere here. We end up with 71 and 36, and we did Taylor expansion over there. With the new Taylor expansion, we move on to the jump step in. Not step in here, step up. I do have a stop here, okay, so just run in. So in the second iteration, we still the same circle, but the new expansion point give us more accurate. Actually, not more accurate. It's a basically expansion. The approximations in different shapes. And we hope we can end up with the solution right here. Does it? So I guess we can make a pause here. Continue. No, it doesn't move up. So I'm curious why it doesn't move up. So I probably need to check the coefficient here. So could do it again. In the second round, something happened. First round is okay. Performing exactly like what we are looking for. Second round, okay, we have update of the linear expansion. Now the coefficients they're both positive. Oh, okay. The objective function changed its direction. Because the circle, the center of the circle was around here. So it changed its. I should move the center of the circle far away, so it's always moving toward upper right. Otherwise, our searching is jumping around from one side of the circle to the other side. Okay, the center, make it 180. How about this? Then it should work. Okay, first round. Okay, we can see it's moving toward the optimal of the linear approximation. Then we are moving out. And second round, the linear approximation of the objective function and also the constraints all changed. And in this new round, we can find it's moving up and then moving. That's the position. That's the position that has the lowers the value. And then third round, okay, all shape changed. And then moving up. This time it's going to the right. Okay, I guess circles are not really good. Because the circles has a, very rounded curvature. So you're like moving, if you move to here, the tangent looks like this. Move to here, tangent move like this. So your solution is like jumping around, never converge. So linear approximation cannot handle functions with this large curvature. This curvy like functions. So I guess it won't converge anyway. Okay, we don't see where the approximation is. I guess we can keep on running and see what happens. If we are lucky, we may be able to. No, I guess not. We are not very lucky. I don't know. We went to somewhere more than 229,000 is not normal because the function is not easy to deal with. I probably have to change it. Let's just use one circle. I think the second one is easier to handle. The first one probably too hard. So maybe x1 plus x2 minus 10. How about this? Make the whole thing easier. Oh, I shouldn't plot the circle anymore. This one. Let me close it. Now I only have one circle. I think the second one. Okay. Is it converging? Converged. Okay. So was it truly the solution? Let me try a greater number, 20. Yeah. This is a much better example. We can plot from the region, we can plot in the region of 30 and 30. Let's observe what happened. Zone, yeah. Okay, let's observe the whole thing again. Yeah, converged. Okay, let's observe from the first iteration. I think this guy, this is the linear approximation of this red circle using 0, 0 as the expansion point. So initially we guess this is the shape of the first constraint. And using linear programming, we end up with a solution right here. Then in the next iteration, second one, with that particular expansion point, we were able to get a closer shape to the circle. So this is the linear approximation based on the solution from the first linear programming. So if we are lucky, we can keep on finding new solutions closer to the linear constraint. And then in this better approximation, we found a solution that is very close to, where is the true solution? True solution is right here. this straight line is my first constraint. The red circle is my second constraint. So this is the point where we have the lowest function value. And in this particular case, we are lucky. During the iteration, the linear approximation is converging, is moving this approximation closer to your true solution. So in this particular case, we're lucky. But in many other previous examples, we may be jumping around. So sometimes solving optimization is quite tricky. Okay? So this is the optimal solution of the second iteration. Now let's take a look at the third one. The third one is even closer. Okay, let's try to plot everything into one drawing and see what's going on. We can plot everything into the same drawing. And I guess the objective function is making people confused. We can turn off the plotting of the objective function. We can turn off this guy. If I do that, I need this hold on. Hold on at here, I guess. Okay. We just turn off. Yeah, no good. Cause I need to turn off these as well. Okay. Save. Okay. So this was the first linear expansion. It's getting better and better. And the slope changed a little bit. If we move closer to the region, right here, right here. So if this circle is being drawn precisely, this is the true solution. This probably is the last linear approximation we made during the iteration, and we end up with a solution right here. Numerically, this probably is the same point compared with the previous iteration. So it stopped. When we perform optimization, we never know where the true solution is. We only compare with what we got earlier. So when the new solution is so close to the previous one, it's like we can no longer improve ourselves. We stopped right here without knowing the true solution is. And from the approach, over here when we perform linear approximation, we couldn't get close enough. So we stop right here. If you want to have even more precise accuracy and you really want to reach to here, what you can do is you can, in this error check, you can tighten this tolerance, because you will allow even smaller tolerance between your current point and the previous point. So let's take a snapshot and let's try to see if we can get, actually we can, from here we know how many iterations. We have, this is 1, 2, 3, 4, 5. So this sequential linear programming was completed within 5 iterations, 5 sequence. Now I tighten this to -6 and see what happened. It will perform even more. Actually, 1, 2, 3, 4, 5. Also 6. Did we reach the true solution? There's one possibility is that the circle was not drawn precisely. What I can do is to truly solve for the true intersection. Let's try that. How do you solve for the true intersection? So solve G1, actually G1, G2. Let's call this X true. I hope this truly solve it. Let's just do this. No. Do you mean? Sorry. Typo. It's like this. No. Here. No. How about this? Really? ELX true. No. Wait, let's just jump in. No, it doesn't. Oh, there are two sets of solutions. Yeah. So so x true dot x1. Yep. There are two sets of solutions because a line and a circle has two intersection points. So if I do this eval x true dot x1, yep, now I have numbers. So the true solution is this guy. Let me call this temp equals to this. Let me just copy this thing here. Let me call this temp 1 and temp 2. And then let me just say the true one. What was that one? Second one. So it's temp 1, second, temp 2, second, and then true error. Norm x true 1 minus our true solution will be the last one. And then display true error. Okay. Just curious how accurate this could be. Why? Why? It was working. It worked, right? No? No need this. No need. We don't need a big bracket. Okay, that was it. Okay. Okay, error was really. Let's see. True solution. 10 point. It was very close. What is this guy? Oh, I should transpose this. I should make it vertical. The error was 7 to the power of negative 15. So close. So the issue was when we plot the circle, all the curve inside MATLAB was drawn numerically. So I guess they used piecewise lines to draw a circle. So the circle was not a true circle. So when we zoom in, we assume this should be a true circle, but in fact it's not. The circle was there. So when we draw the circle, when we ask MATLAB to draw the circle, within this small area, it was not drawn precisely. But now we truly evaluate the solution and then compare, we realize we are so close, so accurate. So, without knowing how the function look like, in this sequential approach, we truly can solve for nonlinear problems. Okay, so this is today I think we are running out of time, and we successfully show you how we can use all these approaches to get solutions. Okay, I guess you care about your take-home exam. I probably will ask you to do something similar to this manually, but not solve to the end. Like in this particular approach, you need to do linear programming 1, 2, 3, 4, 5, 6 times. In my take-home exam, I would say do this probably 3 times or 4 times. And for every linear programming, you probably only need to do 1 or 2 or 3 iterations, like a sub problem. Okay, and in linear programming, actually it doesn't. It's not too difficult, because remember what you need to do for linear programming was only every iteration is like this. You compute this guy, check whether there is something negative. Oh, it's like this guy. This is one example of one iteration. You compute this, find the most negative one, do this, find the smallest positive one, and then swap the basic and non-basic. So this is one iteration in linear programming. So in that particular case, if that's the problem in my take-home exam, let's say the overall iteration requirement is 3, and in that particular case, inside the linear programming, you are required to do 2. So it will converge, right? So totally you need to do all these 6 times. So that definitely can be done within 2 hours. Why not? Just do this 6 times. If you are familiar with this procedure, it's really not taking too much time. Yeah. Okay. And you have 15 hours. That's not expect 15 hours. Okay. Okay, so this time I will be on time. I'm sorry last time I occupy your 1 hour. Okay. Anyway, that's it for linear programming. I will be updating everything to Moodle and Facebook. If you are not familiar with what happened for the following days, make sure you review everything. Try to solve by hand, so in the take-home exam you know how to do.